Hello everyone. My name is Urvi and I'm a software engineer at Microsoft. I welcome you to part 5 of this 5-part series by Scalar, where we are covering linked list data structure end to end. So in this lecture, we'll be looking at another type of linked list which is called circular linked list. After which we'll also see list in C++ STL. Okay, let's start with first of all what is a circular linked list. So far we have seen what is singly linked list, we have seen doubly linked list. The difference was that in singly linked list every node was just pointing to the next node in the list, but in doubly linked list every node was pointing to the next node as well as the previous node in the list. Now what is a circular linked list? A circular linked list is a linked list in which the last node points to the head node. Meaning, if I have a linked list like this, where the first node is the head node, if I make the last node, if I make the last node's next point to my head node, then this becomes a circular linked list. So we know that in the singly linked list that we first studied, the last node's next pointed to null. But in a circular linked list, the last node's next points to head node. Alright, and this could be in a singly linked list. This could also be a doubly linked list, okay, where we have a link to the next node as well as the previous node. That means in a doubly circular linked list, the head node's previous would be pointing to the last node. Okay, so because this is forming a circle, that's why it's called a circular linked list. Now what are the advantages of using circular linked list? First of all, you can start traversal from any point in my circular linked list and still you can traverse through all of the nodes. Also in circular linked list, the advantage comes when we want to traverse our linked list multiple times. Okay, so if it's a normal singular linked list and we want to traverse it, we take a temp pointer and we use it to traverse till the last node. But in case I want to traverse the linked list again, I have to come to my head node and then traverse. But here in a circular linked list, from the last node itself, I can reach to my first node. Okay, so in those cases where we want continuous traversal of our list, in those cases circular linked list comes to our rescue. Now coming to the implementation of circular linked list, let's talk about the node. So the node here, the node structure that we see, okay, in a single linked list, let's talk about single linked list first. In a single linked list, we've seen every node will have two parts. First is the data part where we're storing some value, and the second part is the next, which is a pointer to the next node in my list. So will the node structure change here in my circular linked list? No, the node structure will remain the same. If it's a singly linked list, it will be this. If it's a doubly linked list, then we'll have an additional pointer previous. Okay, so no change in the node structure, just one change would be there. The last node's next would be pointing to my head node. Okay, so let's see how we're going to implement this in code. First of all, creating class node here, and this will be similar to what we have already seen. It will have some int value, okay, whatever value we want to store in each of the nodes, and we'll have a pointer to the next node. So for that we'll have node star next. Okay, and let's also create the constructor here for the nodes. If I'm passing any value d, I want that value in my variable, and then the next should be initialized with null. The next pointer is initialized by null. So this is my node class, and I can use this to create my circular linked list. How can I do that? Let's first create a head. Let's first create some nodes. Okay. So for example, I create n1 is equal to new node with value 1, node star in 2 is equal to new node 2, and I can make n1's next point to n2, and I can make n2's next point to n1. So in this case, you can imagine the n1 pointing to n2 and then the n2 pointing back to n1. So it's a circular linked list with 2 nodes. All right. Let's move forward and see how can we traverse a particular circular linked list. So this might change a bit. Let's first discuss what we were doing in a singly linked list. So when we were talking about a singly linked list where the last node's next was pointing to null, what we used to do was we used to create a pointer, temp pointer we used to call it, and start it at the head node. From the head node we will keep moving the temp pointer till it reaches null. Okay, when it reaches null, we would know that our linked list has ended here, so we'll end the loop. Here, in case of circular linked list, we do not have this null. Okay, what we have is the last node's next pointing to my head node. So what I'll have to do instead, I'll have to check if my temp node reaches my head node again. Okay, if I start my temp pointer at head and while traversing, I reach my temp pointer reaches to the head node once again, that means my entire linked list has been traversed. Alright, so that will be our stopping condition here. Let's write a function void traversal, okay, where we'll be passing the head of my linked list, of my circular linked list. So what we'll do is we'll first of all create a temp pointer starting at head, and instead of using while loop here, we'll use the do while loop. Okay, so inside the do while loop we'll check until my temp is not equal to head. I will keep printing the value of temp, and I'll keep moving my temp pointer forward. Okay, why am I using a do while loop here instead of a while loop? Because I want first this to get executed and then it to check if temp is not equal to head. Okay, if I used a while loop here, then because temp is initially equal to head, it would have never executed the loop, right? And in the end, let's just print an end line. If I call traversal for the current circular linked list, let's create a head pointer as well here, and we'll make it point to n1, and we run this. We get 1 and 2 are the nodes in our linked list currently. Okay, and if you want to, basically see if this is actually a circular linked list that we are talking about, we can create another function, traversal in loop. Okay, just to show you that this is actually a circular linked list that we have created here. And what I'll do here is I'll add a counter while, let's say, it prints the nodes 10 times. Okay, so while k minus minus, I'll do this exact same thing. I'll print the temp value and I'll move the temp to the next node. Okay, and print an end line. So if I do traversal in loop, what will happen? I'll see 1, 2, 1, 2, 1, 2 getting printed repeatedly, right? Because 2 is pointing to 1, then 1 is pointing to 2, then 2 is pointing to 1, and so on. It goes on and on. Okay, so you can now imagine how a circular linked list works, and you can see how we can traverse in it. Of course, we don't want to traverse the circular linked list in loop right now, but just for you to imagine how this will look in code. Okay, now let's move forward and see insertion. How do we insert an element in a circular linked list? And we'll focus really on how this is different from the insertion that we have already seen in singly linked list and doubly linked list. So if I have here a circular linked list and I want to insert a new element at the head position. So what I'll do is, first of all, I'll create my new node. Okay, and I'll have to move my head pointer to my new node, and also make my, first of all, make my new node point to the head node, and then move my head pointer to my new node. But there's another thing that I'll have to change here. What? That is this link, right? So I'll have to make, because I'm updating the head node here, so I'll have to update also this link which joins the last node to the head node. So what we'll have to do is, we'll have to traverse first of all to the last node in my list. Okay, and then once I am at the last node, then I need to make its next point to my new head. First of all, we create a new node, we make its next point to my head, move the head pointer to the new node, and also we change the last node's next point to my new head. Let's see the code for this. Void insert at start node star head and the value that we want to insert in our new node. So first of all, let's create the new node star new node with the given value, and once we have that, firstly traverse to the last node and change its next value. Okay, and for that we'll create a temp pointer starting at head while temp's next is not equal to head. And when will temp's next become equal to head? When we are at the last node. So while this is not true, we'll keep moving our temp pointer forward, and now our temp pointer is on the last node, so we'll make its next pointer point to my new node. I'll make my new node point to the current head, and the head pointer will come at my new node. Okay, so this here we're changing the link from the last node to the head node. Here we're making the new node point to current head node, and here we are updating the head node, which will become our new node. Also, before we start traversing to the last node of our list, let's first check if this current list only has one node, or let's check if this list is empty. When we're trying to insert, if we're trying to insert the first node in my list, okay, that means head is null. In that case, I'll just say head is equal to new node and make the head's next point to head, because there's a single node, its next will point to itself, and I'll return from here. Okay, let's test this. So if I do insert at start head 3 and do a traversal. So I can see 3 got inserted, right? And let's say if head is equal to null and 3 is the first element that I'm trying to insert. Let's see what happens then. Let me comment this out. So I can see that it works if I'm trying to insert the first element when head is initially null. That is our code for inserting at the start, and the time complexity for this would be O of n, right? Because we have to traverse to the last node of our list. Let's move forward and see inserting a node at the end of my list. So here again, if we have a circular linked list where the last node is pointing to the head node, first of all, to insert, we'll create a new node, right? And we'll have to get access to the last node of my list so that I can insert the new node after it. So we'll create a temp pointer and use it to traverse to the last node. In temps next, we'll put the new node, right? So this link will get removed. In my new nodes next, I'll put the head. Okay, so again here we'll have to update the link between the last node and the head node because the last node here is changing, and the time complexity here again would be of n because we need to traverse till the last node of my list. So let's see the code for this. Void insert at end node star head and the value I want to insert. So first of all, let's create the new node. It's equal to new node with the value that is given to us, and I'll add the same check if my head is equal to null, meaning if my circular linked list is empty right now, then I'll just add head is equal to new node, heads next will point to head, and I'll return from there. Otherwise, I'll make a temp pointer starting at head, and I will traverse this till it reaches the last node. So I'll add a check till temps next is not equal to head. Till then we'll keep moving our temp pointer forward. When temp reaches the last node, in front of temp we'll put the new node, and in new nodes next we'll put the head. Alright, so we've added a node at the end. Let's test this. Insert at end, where we are trying to insert 4 at the end of my list, and I also call the traversal function here for my head. Okay, we did not change this back to n1, that's why it was throwing an error. So this was our list, and we added 4 at the end of my circular linked list. So this was insertion at start and end. I am not discussing insertion at the middle because that would remain the same as what we had seen in singular linked list, right? The change in circular linked list, the difference in the circular linked list comes when we're talking about insertion or deletion at the end of my list or at the start of my list, right? So if we're talking about updation at some kth node, insertion or deletion at some kth node, that will remain the same as we have seen before. Okay, so let's discuss now deletion. What happens when you try to delete a node from the start of my circular linked list? So this means I am trying to delete my head node. In this case, firstly, what we should do is make the node that needs to be deleted pointed to by a pointer. So let's say temp is pointing to the node that is to be deleted. After that, I need to change this link, right? Because this link points to the head. The last nodes next points to the head. Now head will get updated because head is getting deleted. So I need to update this link as well. For that, again, we'll have to traverse to the last node. Let's use a pointer called tail to traverse to the last node of my list. And then I can change this link and I say, okay, now make the tails next point to heads next, and then I can move my head pointer to heads next. Once I've done that, then I can free up my temp node. The time complexity here would be O of n because I'm traversing till the last node of my circular linked list. So let's see the code for this. Void delete at start node star head. So first of all, let's say, okay, the node that needs to be deleted is my head node, and to traverse to the last node, let's create another pointer tail. So while tail next is not equal to head, we'll keep moving the tail pointer forward. Now my tail is pointing to the last node of my list. Once it reaches the last node of my list, then I'll make its next point to my current heads next. I'll move my head pointer to heads next, which will be my new head, and finally I can free up temp. I can also add a check here. If my head is my heads next is equal to head, meaning I only have one node in my list, okay? If there is no node, okay, if my list is empty, then I can simply return, okay? If the list is empty, I don't need to delete anything. But if my node has if my list has a single node, okay, in which case I can test by checking if heads next is equal to head. If this is the case, then we can just free up my head node and return from here. Okay, I don't need to do anything else. So let's test this. Delete at start, and let's see the traversal after it. So right now I have 3 at the start of my list, and we can see it got removed, it got deleted from my circular linked list. Okay. Coming to deletion of a node from the end of my circular linked list. So again, I have a circular linked list and I need to delete the last node. I need to delete the last node. So in order to delete the last node, we'll have to make changes to the new last node. After I delete this node, what will be the new last node? That will be this second last node. Okay, so first of all, let's call this second last node. Okay, we'll use a pointer second last to point to this, and this will be my last node. So last node is the node that I need to delete. Once I have reached to the second last node, I will change its link, its next link to point to my head, and once I've done that, then I can easily free up my last node. Okay, and again here the time complexity of O of n because we're traversing till the second last node of my list. So delete at end node star and head. Okay, the initial checks will keep the same. If my head is equal to null, if it's empty, we'll return. If heads next is equal to head, if there's only one node, in that case we'll just free up the head and return. Else we'll create a pointer. Let's create a pointer second last starting at head, and while second last next is not equal to head. So when I reach the second last node, its next will be equal to head. Till then, I'll keep moving this pointer forward. Once I've reached, I'll create another pointer for the last node, which will be second last node's next. I'll make the second last nodes next point to my head node, and then I can free up my last node. Okay, let's test this. Delete at end. Traversal. Okay, so now here we can see 4 got deleted from the end of my list. Okay, so that's how we delete a node from the end. We've seen insertion, we've seen deletion, and we've particularly seen how to handle these operations when there's an operation happening at the start of my circular linked list or the end of my circular linked list, because that's when you'll have to keep in mind that okay, this is a circular linked list and I need to make the last node's next point to my head node. Okay, great. Let's come to a coding problem now and try to solve a coding problem on this topic, circular linked list. What does the question say? The question says we are given a circular linked list and we need to split it into 2 halves. Okay, and if there are odd number of nodes, then first list should contain 1 extra. Consider this is a circular linked list that is given to us, and we need to split the circular linked list into 2 circular linked lists. So the output would come out to be something like this. Okay, and this is in case of even number of nodes. If we have odd number of nodes, something like this, in that case what should be done? The first half of the list should contain 1 extra node, right? So in that case, these will be the 2 circular linked list, okay, the 2 halves of the bigger linked list. In order to divide this linked list, the circular linked list, into 2 halves, we need to know what is half of the circular linked list, and for knowing the half, we need to know the middle point of my linked list, right? And now if you remember, we did discuss how to find the middle point of a linked list. We did that using slow and fast pointer approach, where we said that if the slow pointer is moving by 1 node and the fast pointer is moving by 2 nodes, then in the same time, slow pointer will cover half the distance as the fast node, right? So if the fast node reaches the end of the list, at that time my slow pointer will be at the middle of my list. Make sense? So if I have my slow and fast pointer starting from the head and I move my slow pointer by 1 node and fast pointer by 2 nodes, when my fast pointer reaches the end, the slow pointer will be at middle. Let's see that. In the first iteration, we'll have my slow at 2, fast at 3. In the next iteration, I'll have my slow at 3 and fast at 5. So now here you can see fast has reached 5, which is the last node. In that case, I can say that my slow pointer is now at the middle of my linked list, which is at 3, right? So from here, I need to divide my list. Now I need to divide my list into 2 circular linked lists. To divide it into 2 circular linked lists, let's create the heads of those 2 circular linked lists. So the head of the first circular linked list would be at the original head. Let's call it head 1. And the head of the second circular linked list would be at the next of my slow pointer after my middle node. So let's call that head 2. Okay. So now I have the heads, the starting point of my 2 circular linked lists. Let's now decide what will be the last node of these 2 circular linked lists. So for the first half of the list, the last node is the middle node, which is being pointed to by the slow pointer. So what we'll do is we'll change this and we'll say make the slowest pointer next point to my head 1. Okay, so I have my first circular linked list here. And similarly, I'll say make my fast pointers next point to head 2. So I have my second circular linked list here. So I've divided my circular linked list into 2 circular linked lists, right? Again, if we have even number of nodes, let's say something like this, what will happen in this case? If I have my slow and fast pointer here, in the next iteration, when slow reaches here, fast will be at 3. When slow reaches 3, fast will be at 5. Now, in case of even number of nodes, we will stop when fast pointer reaches to the second last node, because after this it will come back to my head node, and I don't want my fast pointer to come back to my head node, so I'll stop here. Now, when fast has reached the second last node on the last node, we will stop and we'll say, okay, now my slow pointer is at my middle node as it is here. So we'll define our 2 heads. Head 1 will be at original head, head 2 will be at the node after slow pointer. We'll make the slow pointers next point to my head 1, and for the last node of the second list, we'll first of all move my fast pointer to the last node, and then I'll say, okay, now make the fast pointers next point to my head 2. So again, I have my 2 halves of the list here, right? And the time complexity here of this solution would be O of n, because we are using, we are traversing the entire linked list to find the middle node, right, using my slow and fast pointers. So let's try to implement this now. Let's create an input list for us. Node star head is equal to null, and we'll use the insert at end function to insert some nodes in my circular linked list. Let's see what this linked list looks like. Okay, so to divide it into 2 halves, let's create 2 new heads, head 1 and head 2. Okay, and this head 1 and head 2 should be pointing to the head nodes of the 2 circular linked list. That would be the halves of this circular linked list over here. So let's create a function split linked list, where we'll pass the head of the original linked list and we'll pass the new heads, head 1 and head 2. And after we have solved this, after we have our head 1 and head 2, our 2 circular linked list, that will be the 2 halves of the original linked list, we'll call the traversal function on it. Okay, so let's now write our function split linked list. The first is the head of the original linked list. Second is the head of the first part of the linked list. And by the way, the original head and the head of the first part of the linked list will be the same, right? So you can either keep it the same or you can create another, pointer for it if you want, for clarity. All right, so the first thing that we do is we find out the middle node. Okay, finding the middle node. So for that we create 2 pointers, slow and fast, starting at the head node. While fast's next is not equal to head, meaning it is not the last node, and also fast next is not equal to head, meaning it is not the second last node. Till that time, we'll keep moving slow pointer by 1 node, and we'll keep moving my fast pointer by 2 nodes. Alright, so now my slow pointer is pointing to the middle node. So let's define the new heads, placing the new head pointers. So head 1 will be at the original head and head 2 would be at the next of the slow pointer. Also, in case of even nodes, we will move the fast pointer to last node. Okay, we can check if fast next is equal to head, meaning it is at the second last node, then we'll just move the fast to its next node, which will be the last node. Okay, now we are making the last nodes point to the head nodes. So the last node of my first half of the list would be pointed to by the slow pointer. So I'll say slow's next should be head 1 and fast next should be head 2. For edge case, we can keep a condition if heads next is equal to head, meaning there's only one node, then we won't do anything, we'll just return. Okay, we can say head 1 in that case is equal to head, and head 2 will just keep null and return from here. Okay, this is if list only has one node. Okay, so let's try to run this. So you can see this was my original list and these are the two halves of the list, 1, 2, 3, 4. And let's also check for odd number of nodes. If I add another node here, 1, 2, 3, 4, 5, then my first half of the list is 1, 2, 3 and the second half of the list is 4, 5. Alright, so our code works perfectly. Moving forward, we will be looking at lists in STL C++. So what is STL here? STL stands for Standard Template Library. It is a library of template classes in C++ which has implementation of the commonly used data structures and algorithms. And list is one of the template classes that is present there. Alright, so we can say that list is the template class in standard template library for doubly linked list. Now what this means for you is that whatever we've seen, right, how we create a class node, we define what are the properties of the functions, we wrote all of the insertion, deletion, updation, reverse functions for our doubly linked list. All of those functions, all of those implementation is built in and given to us by this STL library in C++ that we can leverage in code. So list is a template class for doubly linked list. Okay, doubly linked list where every node will have access to its next node and its previous node. Now if I want to use this list in my code using STL, what do I do? First of all, I need to include the list header file. Hashtag include list. Okay, this list will allow me to create a list and also use all of the functions on this list that are built in. And if I want to create a list, I can specify list, the data type of the values that I want to store in the list, and the list name. Okay, so it's as easy as saying list int L1. This will create an list for me called L1, a doubly linked list called L1, in which I can store integer values, and I can also initialize it at the same time by putting some values in my curly brackets. Okay, so it is that easy to create a doubly linked list in code using STL. Now you might be wondering, if it is so easy to do this, if it is so straightforward, why did we go through all of these previous videos and saw how to implement doubly linked list and how to implement all of the operations on it? That is really important, because once you understand how doubly linked list was actually working, that's when you'll understand how list in STL works. Alright, and number two, when you're going for interviews, DSA interviews, the interviewer might ask you to actually implement the doubly linked list and not just use the list present in C++ STL. So you should be knowing the implementation of singly linked list, doubly linked list, and all of the operations. But if you are given a problem and if you're given the freedom to use any data structure that you want, and you're looking for something like linked list, this list can come to your rescue and you can use it without any without implementing the functions. A lot of these functions we'll see right now in this list are implemented, they are inbuilt inside the C++ library for us to use. Let's look at first of all some of the iterator functions that we have on our list. So the first one here is begin, and what begin returns is an iterator to the first element in my list. Okay, now what is an iterator here? Iterator you can you can understand by thinking of pointers, just like we talked about pointers. So they are pointer like, and what iterators do is they help us to access the elements of a particular STL container. Okay, so list here is an STL container, a container which is being used to store some values. Okay, and to access the elements or the values that are being stored in this STL container, we make use of iterators. Okay, not just list, we use iterators in other STL containers as well. Could be stack, queues, vectors, sets, etc. Begin function will return me the iterator to the first element. So if I have a list 1, 2, 3, 4, and this is a list L1, and I say L1 dot begin, then this will return me an iterator to the first element, which is 1. Okay, it will not return me 1 but an iterator to 1. So to access it or to print its value, I'll do star iterator. Okay, if I am writing iterator is equal to L1 dot begin, then to print the value of iterator, I will print star iterator to access the value that this is referring to. Okay, similarly end will return me an iterator to the position after the last element, So if I have a list 1, 2, 3, 4, L1 dot end will return me an iterator to the position after my last element, not to my last element but the position after my last element. Remember that. Similarly, we also have r begin and r end functions. What they do is r begin will return me iterator, or let's say it will return me a reverse iterator to the first element in reverse iteration. What do I mean by that? So again, if I have a list with 1, 2, 3, 4 values and I ask for L1 dot R begin, then this will return me an iterator to 4. Okay, so basically R begin will return me an iterator to the first element in the reverse iteration. When I iterate this list in the reverse manner, what would be the first element? The first element would be 4. So that would be returned to me by L1 dot R begin. And R end, what this will give me is, this will give me a reverse iterator to the position after my last element in reverse iteration. Again, so if this list is reversed, what would be the last element? 1 would be the last element. So R end, L1 dot R end will return me an iterator to the position after the last element, which is 1 in this case in reverse iteration. Okay, so these are some of the iteration functions that we'll be using to iterate. One last iterator function is advance, and this is used to move my iterator. So in the advance function, I pass the iterator and I pass n, okay, some integer value, and what this will do is this will move my iterator by n places. So for example, in my list 1, 2, 3, 4, I have an iterator to 1, okay, called ITR, and I say advance ITR by 2 steps. So this will move my iterator to 3. Okay, let's look at these functions in code now for better understanding. To create a list, we've included the header file for list, and now I can create a list of type int with some integer values. Now if I need to access the first element of this list, I can use an iterator. Now how do I get an iterator or define an iterator to this list? I can either say list int iterator and the iterator name L1 dot begin. Okay, so either I can mention the iterator data type like this, I can mention the iterator and what type of iterator I want. I want an iterator for this type, list of type int, or I can just say auto iterator in this case also, because this is, I'm saying this is equal to L1 dot begin, so it will be able to derive that this is an iterator for type for a list of type int. Okay, and to print its value, I can say star int so you see 1 got printed here because that is the first element of my list. Now suppose I create a reverse iterator. Okay, let's call it a reverse iterator L1 dot R begin. So this will give me an iterator to the first element in the reverse iteration. That means 4. Okay, and if I print this, what is getting printed? 4 is getting printed, right, as it should be. I can also try to move my iterator. So if I say advance my iterator by 2 steps, okay, so now if I print, let me comment this out. Now if I print, my iterator is at star iterator is printing 3 because my iterator now has moved from 1 to 3, right? So I can use the advanced function for that. Next, let's discuss how do we traverse a list, okay? And let's see this in code directly. Two ways to traverse a list. First is range based or loop based. So what we do is in the loop, we basically use a for each loop. So for auto number in my list 1, print num. All right, and let me comment out the above code. Okay. So you can see 1, 2, 3, 4 got printed here. I was able to traverse and print all the values of my list. So this is the range based way to do this. Another way to do is through iterators. Okay, and how do we do that? For that we use a for loop. So for auto iterator, which will begin at L1 dot begin, the first element, and this will go on till my iterator does not reach L1 dot end, which will be the end of my list. Okay, this is the position after the last element of my list. ITR plus plus. So I created an iterator to traverse my entire list from L1 dot begin to L1 dot end, and I will print star ITR here. So you can see again here we are able to see the traversal of my list. We can also traverse it in the backward direction. How can we do that? For that we just need to change this from begin to R begin and from end to R end. So now it will traverse in the reverse direction. Okay, let me run this and you can see here 4, 3, 2, 1. This is the reverse direction of my reverse traversal of my list that I've created. Let's talk about inserting elements now. To insert elements, we have a function called insert. Okay, if I want to insert any value into my list, and in the insert function we pass the iterator and the element. What this does is this will insert the element before the iterator. Okay, so if I have a list 1, 2, 3, 4, okay, and I say L1 dot insert, where I'm passing an iterator that is pointing to 3 and I'm passing the element as 5. What this will do is this will add 5, insert 5 in my list but just before 3. And I can also pass another parameter here in this function just called count. If I pass count, by default this is 1. If I pass any value of this, then it will insert that many number of elements. Okay, so if I am passing iterator to 5, so this will insert 5 2 times for me before 3. Okay, and another way to insert is when I want to insert a range of elements. So there I can pass a start iterator and an end iterator. What will happen is, suppose again I have a list and I have my start iterator here, S iterator, and I have my end iterator here. So what this will do is it will insert values starting from start iterator to end iterator but not including the end iterator. Okay, exclusive of the end iterator. This will insert this value, this range of values before the iterator that I pass. Okay, let's see this in code. inserting elements. So if I say L1 dot insert, let me first create an iterator. So I create an iterator at starting at L1 dot begin, and then I advance it by 2 steps. Okay, so now it is pointing to 3, and then I say L1 dot insert the iterator and the element that I want to insert, which is 5. Let me print the values again. So you can see here 5 got inserted just before 3 because I passed an iterator to the value 3. If I add another parameter 2 here, I pass the count here, so this will insert 5 2 times for me. Alright, and here if I pass 2 iterators, a starting iterator and an end iterator. Let's say I pass or start iterator L1 dot begin, and I pass an end iterator L1 dot end, or let me advance it from begin. So I'll move my advance, using advance I'll move my end iterator to 3. Okay, and here I'll pass my start iterator and my end iterator. So let's see what happens. So I passed a start iterator that was pointing to 1 and end iterator was pointing to 3. So from start to end, not including the end element, this will get inserted, meaning 1, 2 will get inserted just before 3. Okay, so this is how I can also insert a range of values in my list. Moving forward, we can also delete elements using erase function. So in the erase function, we pass the iterator, and that element to which the iterator is pointing, that will get deleted. So if I have a list and an iterator to 3 and I say L1 dot erase iterator, this will remove 3 from my list. In the erase, I can also pass a range of values using start iterator and end iterator, just like we saw while inserting. We can pass start iterator and end iterator. This will erase values or elements from start iterator to end iterator. Okay, this means this is not including the end iterator. Okay, so excluding end iterator value. Okay, let's see this in code. So if I'm saying L1 dot erase, okay, and again I'm passing the above start iterator and end iterator that we defined, and print the list again. So let's see what happens. So I pass in start iterator at the end, and let me actually move this below so we're able to see this. Okay, let me rename this, or let me get rid of this. Okay. So you see here what happened was 1, 2, 3, 4, this was my original list, and I passed a start iterator at 1 and an end iterator that was pointing at 3. So from 1 to 3, not including 3, so only 1 and 2 got deleted from my list. Similarly, if I pass just one iterator here, for example, I just pass the start iterator, what will happen in that case? Just the first element will get deleted, 1 will get deleted. Okay, so this is how we can insert elements, delete elements, traverse elements in my list. And there are a couple of other functions as well, member functions for list. For example, the front function returns the value of the first element if you need the first element of my list. The back function returns the value of the last element. Push front will add a new value to the start of the list. Push back will add value to the end of the list. We've seen all of the operations for this. Pop front will remove the first element, pop back will remove the last element, size will return the size of the list, empty returns if the list is empty or not, so 1 if the list is empty or else 0, and reverse is used to reverse the list. So most of these operations we have seen, we've actually implemented these ourselves for linked list, but these functions are inbuilt which we can use directly when we are using STL. So although you won't find a lot of even practice questions on C++, on list STL in C++, but just for the fun of it, you can try some of these functions. The questions that we've already done, we've seen in linked list, you can try a few of them out using STL. But remember this, in your interviews, in your DSA interviews, you will be asked, most probably you will be asked to implement the linked list. So remember how to implement it and all of the implementation of all of the operations that we have seen so far. Amazing. Thank you so much for watching this, and that's all for this video where we covered circular linked list and we covered list STL. And that's all for this video. Thank you so much for watching. Do practice all of the questions that we discussed in this module, and if you have any doubts, drop them in the comments so that we can get to them.